today I'll go over a limit at infinity and see how limit at infinity works, and then what is the horizontal asymptote. So limit at infinity means that, first of all, we denote it either by this or that. And it basically says that what is the number. So if this is L and number, so for this one, values of f gets as close as we want to L when x is large enough. And the same thing starts here, but this time as x grows very big, negative number. So in terms of the graphs, so this means that there's a L. As we get further away to the right, the function gets closer and closer to that number. This getting closer could be different forms. For example, we could have something getting closer like that. That's a pen that my daughter uses for her works on my tablet. So it's so nice and shiny and rainbowy. Or could be something like this. So could intercept and then gets closer and closer to that line. Well, that's when x goes to plus infinity. For x going to negative infinity is also the same thing. Well, this time we are going this way. Well, there is a very nice fact that tells that this infinite limit can be turned into one of these regular limits when x approaches to some number. And that is limit of the function as x grows to plus infinity is nothing but limit of the function, replace x by 1 over t and let t go to 0 plus. So x is 1 over t. So if you replace t by 1 over t and then find the limit as t goes to 0 plus from the right-hand side to 0 from the right-hand side, that will give us the same result as the function, the limit of function as x goes to plus infinity. For the negative infinity, the same story goes ahead, but this time we have to let t go to 0 from the left. Okay. Well, as a result of this, we see that the limit laws and squeeze theorem. Okay, so we have to be a little bit careful about the squeeze theorem, but it's very similar work for limit at infinity. Some more facts about the limit at infinity is like, okay, so if you have limit of 1 over x as x goes to plus or minus infinity, this is equal to 0. And indeed, while using this fact, you can show that if this is x to the power alpha, for any alpha bigger than 0, it still will be 0. Limit of exponential function b to the power x as x goes to plus infinity. This is 0 if b is less than 1. And limit of b to the power x as x goes to negative infinity is equal to 0 if b is less than, bigger than 1. And these can be seen just by looking at the graph of the functions. So this is b when b is bigger than 1, and this goes to negative infinity. the function gets closer to 0. There is a same kind of story, but the other way around. Oops, that's not good. That's the same point. So when b is less than 1 and bigger than 0, this happens there. Well, you can see tan inverse also works in this way. So limit of tan inverse, I'll just write, and but you can see it based on the graph of tan inverse. This is pi over 2, limit of tan inverse x as x approaches to negative infinity is negative. So this is very fast review of the whole facts that are involved here for the limit at infinity. As for the naming, just keep in mind we have infinite limit. That's when we approach x approaches to a number, but the result is infinity. Limit at infinity is the other way around. X approaches to plus or minus infinity, and the result, the limit value, is L. Okay. We have also infinite limit at infinity. When x goes to plus infinity, the limit is infinity or minus infinity. Alexandra, yes, please.
I'm not sure if like you can answer this, but I just have a question kind of like about the assignment. So if something was like the limit of tan inverse times another thing, but it didn't have the x in it, how would that work?
Can I answer that question? I'm thinking. Maybe can you wait to the end of the session and let's talk at the end?
Sure, thank you.
Yes, well, just make sure that you're not confusing the value of, so evaluating tan inverse onto another function, like tan inverse of, say, something like, I don't know, x squared minus 1. This is composition. Instead of x, we have x squared minus 1. So you should not confuse these two things. But at the end, please, let's just talk about this one at the end, okay? Let me see some examples. Okay, so one of the cases that you will notice we have is when you're trying to find limit at infinity of a rational function. So for the rational functions, when you try to use the infinite, the limit laws, it just stops at the first step, because limit of x squared is infinity as x goes to plus infinity, and minus 3x as x goes to plus infinity is infinity. So you cannot subtract infinity from infinity. Done. You're not. This is the limits at infinity does not exist. So you cannot limit. You cannot use limit at infinity or limit laws for limit at infinity. But well, this will turn out to be infinity over infinity. This is different kind of indeterminate form. We will discuss this more later in the applications of derivatives. But here I want to just go over some tricks that will help us to evaluate this. The way it works is this, that I want to use this fact as x goes to plus or minus infinity, this is 0. I want to generate terms which are like this or multiples of this. And for that, I factor out, or I divide, I would say factor out. It's a little bit strange word to use here. The highest powers of x from the numerator and the denominator. Well, this means that you're dividing each term by the highest power and multiplying the whole thing by highest power. And well, this really means that, you see, I can start canceling before I do anything. So I can cancel that, that one, there will be one here and that one. So the result, at least for the second part, will be 1 minus 3 over x plus 2 over x squared, and 1 minus 2 over x plus 1 over x squared. Yes. And also I have a term like this at the beginning. So I put these two guys together and I see that, oh, okay, this is, I can cancel this with that, 1 remains, and this is nothing but limit of 1 over x. Since I can now compute the limit of both of these guys, I can use limit laws here and separate this one. Find limit of the first one, find limit of the second one, multiply at the end. Here, then when you apply limit laws, you see that 3 over x is nothing but 3 times limit of 1 over x. One of the limit laws gives me this, and while this part is 0, 3 times 0 is 0. So that means that this will be 0, this will be 0, this will be 0, this will be 0, and this will be 0. So this means that this is 0, 1 minus 0 plus 0 over 1 minus 0 plus 0. Limit laws are applied here. And this will give me just 0. So the limit is 0 in this case. Alexandra, do you have a question, or you forgot to lower your hand there?
Oh, sorry about that. I forgot to
No
lower
worries,
my hand.
no worries. Any questions, any comments? Okay, so I will yeah, let me see what was the third example. Okay, I'll do the second example and third example, leave it as the as something for you to complete. Okay, here the same story goes. It's a rational function. I want to factor out the highest power so that I can use the fact that limit of 1 over x to the power alpha with the positive power always is 0 as x goes to plus or minus infinity. So in this case, this will be 1 minus x plus 2 over x cubed. I'm doing some part of those calculations that I had before, but this time a little bit faster. And now I have limit of x goes to negative infinity. You see, this guy, I factor out x to the power 5 from numerator and the denominator, and these guys are canceling each other. The remaining is nothing but very nice limit for which, to evaluate which, I can apply limit laws. And this is 3, so this is again limit laws. 3 minus 0 plus 0 minus 0, 1 plus 0 plus 0, and that gives me 3. So the limit of this guy is equal to 3. And the same story works always when you have some versions of polynomial in the numerator and denominator, and you can always factor out the highest power from numerator and denominator and use the fact that limit of 1 over x to the power alpha is 0. Any questions, any comments before I go? Adam, yes, please.
Hello, Professor. Is it possible to factor out 3x to the power 5?
Sure, definitely. Well, that would still work. Well, a little bit different middle steps, but the end you'll get the same thing. Yes.
Okay, thank you.
Okay. So this one I will leave it as do it yourself example. You can take a screenshot of that and and do it later in your own time. I also do this one. Okay, so it's not rational function anymore. In the numerator, we have an irrational function divided by a polynomial. But irrational functions are very close to rational function. It means that there is still some kind of polynomial structure in these functions. In other words, I can still consider everything happening under this square root. Forget the square root for a second, and then you have a polynomial down there. And the same trick can be applied here with the difference that you have to always be careful of using the square root. So I'm factoring that. The highest power is this, yes. And x1 plus 1 over x. Now, oh, there's x squared there. Yes, I factored out x squared. This is nice. And then you go ahead, before I do any calculations, I have to kind of get rid of these factors that I factored out. And then, well, I say that, okay, nice. Root of x squared times something is root x squared times root that something. The assumptions of both of them are positive, yes. Now, root of x squared, what is root of x squared? Can anyone tell me?
Absolute value of x.
Absolute value of x. That's the voice I like to hear. Absolute value of x, not x. So here, then that means that this absolute value of x will come out 1 plus 3 over x minus 1 over x squared, x1 plus 1 over x. Before we do the simplification and apply the limit laws, we have to be careful here now. I am trying to use absolute value, a formula for absolute value. Absolute value is piecewise defined function, and it is positive when x is bigger than or equal to 0, and it is minus x when x is a negative number. Here now, since x approaches to negative infinity, it means that we are working with very large negative numbers. So when x approaches to negative infinity, it means that if you want to use a formula for absolute value of x, you have to replace it by negative x in this case, because the function, the x approaches to negative infinity. So that means that I have minus x over x, and I can separate these two guys now. Yes, I'm doing at the same time part of limit laws here as x goes to negative. Now, before I do apply the limit laws, I can now simplify this. This first part will give me -1, and the second part using again limit laws. This will give me 1 plus 0 minus 0, 1 plus 0, and that is negative root 1 over 1, which is just negative. And again, here it shows a very important fact that absolute root of x squared, you should not bluntly put it as x. It is absolute value of x. And when you're dealing with absolute value of x, it really matters if you're working with negative numbers or you're working with positive numbers. But when x goes to negative infinity, that's just very nice and fixed fact. And you should note that if I do the same limit for the same function, but this time x going to plus infinity, if I do the same steps, absolute value of x won't be any more equal to negative x. It will be equal to x itself, and the result will be 1. So that really shows that figuring out the right sign there can change the result of our computation. Okay. Any questions? Any comments here? Okay. Example 4. This is nice. Yeah. When x goes to plus infinity, you should see that limit of 2 to the power x as x goes to plus infinity. This is exponential function. The base is 2 and it's bigger than 1. This is plus infinity. And limit of tan inverse of x as x goes to plus infinity. This is pi over 2. Now, one function getting closer to pi over 2, a number. The other function grows and grows, big and big and big and big. You add these two things. This is just close to pi over 2, and that guy is growing big and big. You add this number, which is very close to pi over 2, to a number which grows high and high, big and big, and large, the whole process will continue. So as a result, this is not limit laws. This is just an argument that we are putting out there, saying that, okay, if this number is growing high and this number is something around pi over 2, and add them, it's still growing very fast, right? So that will give us the limit of 2 to the power x plus tan inverse of x as x goes to plus infinity is infinity. Well, the other limit is a little bit maybe more interesting. Well, I don't know what is more interesting. Maybe the one which is plus infinity is even more interesting because you can still talk more about that. This is done here because this case, this will be 0 plus minus pi over 2. This is negative pi over 2. It's just extra piece there just to show you. Any questions, any comments there for me? Alexandra, yes, please.
So for that one, why was the limit as x goes to negative infinity of 2 to the power x 0 instead of negative infinity?
Oh, you look at the graph of 2 to the power x. Exponential function never goes below x-axis, so it is never negative. So it is like this, 2 to the power x. As x goes to plus infinity, the function grows to plus infinity. As x goes to negative infinity, the function goes down closer to 0.
Thank you.
Okay. So horizontal asymptotes, this is just the definition. Remember, the vertical asymptotes are vertical straight lines. So the equation for vertical lines are x equal to a number. Horizontal asymptotes are horizontal lines, straight lines, and they are given, their equations are y equal to a number. So a line y equal to a number L or B is called horizontal asymptote if when x approaches to plus infinity, goes to plus infinity, the limit of the function at plus infinity is b, or limit of the function at negative infinity is b. Any of these ones happens, you get b. There are 2 points here to note. First of all, is that we can have at most 2 horizontal asymptotes. Every function can have at most two horizontal asymptotes. Because there are two limits to consider as x goes to plus infinity, as x goes to minus infinity. If this is a number, another one is a different number, then we have two horizontal asymptotes. Compare this to the vertical asymptotes. Vertical asymptotes, you can have infinitely many vertical asymptotes, like tan x has infinitely many vertical asymptotes. The second thing is about computing. Remember, in the vertical asymptotes, we have to find candidates for A, at which as x goes to A, well, the function blows up to a positive infinity or plunges down to negative infinity. Yes, we have to find candidates. So that's the first step. Remember, in the case of rational functions, we went and listed all the roots of the denominator and find the limit and see if they're positive infinity or negative infinity. In the case of the horizontal asymptotes, you only do two limits, and you don't need to be worried about what are the candidates. You just, to find them, meaning that the horizontal asymptotes, we only need to study two limits at infinity. Limit of the function as x goes to plus infinity, it can give us a number or no number. Negative infinity can give us a number or no number. So we can have no asymptotes, horizontal asymptotes, one or two horizontal asymptotes. So that's just very quick review of the definition. And if you know how to find limit at infinities, that will give us the horizontal asymptotes. Is there any questions, any comments before I move to the examples? Okay. So here we are looking for the horizontal. So we go ahead and try to find limit of this guy as x goes to plus infinity. Well, we already did an example like this. Since we are dealing with a function on its numerator, we have kind of some level of a polynomial structure, and in the denominator we have polynomial. So we can use the trick, factor out the highest power. So I do the same thing as we did before. I will first do for the square root part. Well, I have plus x still staying out there. Yep. And this is when x goes to plus infinity. Actually, this is the same computation if x goes to negative infinity as well. Yes. And while here, then absolute value of x comes out 1 plus 3 over x minus 1 over x squared plus x over x 1 plus 1 over x. As x goes to, again, plus or minus, doesn't matter. This type of calculation will be done for both. Here is what will make difference. If x goes to negative infinity, absolute value of x is negative x. So I will have limit of x negative infinity. This is minus x root 1 plus 3 over x minus 1 over x squared plus x. And this then, okay, now I can factor out the x's here. And I get minus 1 plus 3 over x minus 1 over x squared plus 1 over x 1 plus 1 over x. Yes. And then I can cancel these two. and use limit laws. This will go to 0, this will go to 0, this will go to 0, and then I will get negative 1 plus 0 minus 0 plus 1 over 1. This is negative root 1 plus 1 over 1, which is 0. So as x goes to negative infinity, the function has limit 0. So y equal to 0 is a horizontal asymptote for that. How about x when x goes to plus infinity? In that case, absolute value of x is equal to x. And the computations that we did here will repeat itself with the difference that now I don't have the multiple negative sign multiple for our square root in the numerator. So then I can factor out x. I'm doing a little bit fast, I understand, but I hope that you have seen enough of all these works now in this session that you can just go and do it, the details yourself. Well, sorry, this was for plus infinity. And then, okay, so this goes to 0, this goes to 0, this goes to 0, and the limit is root 1 plus 0 minus 0 over 1 plus 0. Oh, there was a 1 plus 1 in the numerator as well. So this is root 1 plus 1 over 1, which is just 2. Okay, so limit as x goes to plus infinity is 2, so y equal to is a horizontal asymptote. And that's it. That's what we found. 2 horizontal asymptotes for this function. As x goes to negative infinity, we have 1. As x goes to positive infinity, we have another. Any questions, any comments? Relo, yes, please.
Oh, wait, I think my question was answered after looking at it.
Okay, okay, perfect. Any other questions? Any other comments?
I was just wondering quickly why the x at the end of both of them turns into a 1.
Because that's just x. I'm factoring out x here. And see, this term has 1x, 1 times x. This term has this whole square root multiplied by x. If I factor out from the first one, this square root remains. From the second one, 1 remains. From the beginning, x was outside. So x is x. It's not absolute value of x. So for both of them, we'll still stay in the x. Did I answer the question? Or...
Yes, thank you.
Okay. Okay, another example. Oh, I like this example. You see, in the previous example, we used the fact that 1 over x to the power alpha as x goes to plus infinity or minus infinity is 0. Yes, that was the calculation we did. But now I want to use the fact that limit of b to the power x as x goes to plus infinity is 0, as if b is between 0 and 1, and limit of x going to negative infinity, b to the power x is 0 if b is bigger than 1. Compare it to limit of 1 over x to the power alpha is 0, no matter if x goes to plus or minus infinity. Okay, so this already tells me that, okay, if this is the trick that will work, it has some we need to do different things for for the limit at plus infinity and for the limit at negative infinity. And how does this work? Okay, so I want to cook up 2 to the power x minus 3 to the power x over e to the power x plus 5 to the power. I want to cook up some exponential functions which work nicely here. By that, I mean that, okay, I know that 2 to the power x goes to infinity as x goes to infinity, plus infinity. And 3 to the power x goes to infinity as x goes to plus infinity. But I know that 3 to the power x goes faster to infinity than 2 to the power x. Yes. I hope that this makes sense. 3 to the power x grows faster. And that way I can kind of get idea that, okay, remember in the case of x squared plus 3x, we found the term x squared, the highest power, which goes faster to plus infinity as x goes to plus infinity. And we factor out all of those ones. Now here, I will do the same work, similar work, not the same, similar work. So in that case, this will be this. And in the denominator, the highest base is 5 to the power x. Okay. But then, okay, so I see there are nice things coming our way. But how about 2 to the power x over 3 to the power x? This is exactly the mathematical way of seeing how 3 to the power x goes faster or grows faster as x goes to plus infinity than 2 to the power x. And this is how we do this. This is the same thing as 2 over 3 to the power x. And 2 over 3, this is an exponential function. Now the base is less than 1. I factored out the exponential term with the highest power, and it turned out that the factored terms are going to be again exponential functions, but the base is going to be less than 1. And when the base is less than 1, as x goes to plus infinity, this will be 0. And I'm going to use that fact here. So limit of x goes to plus infinity. Now I have 3 over 5 to the power x. I have limit of 2 over 3 to the power x minus 1. We have limit of e over 5 to the power x plus 1 as x goes to plus infinity, as x goes to plus infinity. Yes, and as you can see, this guy will go to 0, this guy goes to 0, this guy goes to 0, and this is 0 times 0 minus 1 over 0 plus 1, which is just 0. So this computation shows that y equal to 0 is a horizontal asymptote for the function g. I have computed only plus infinity limit. How about the limit at negative infinity? That's a different story, and you will notice right away why it is different. Is there any questions, any comments so far? Brandon, yes, please.
I was just wondering, for the assignment, did we have to show that law or that fact, or is it kind of something we can assume?
Which fact? Sorry, which one?
For limit x to negative infinity bx equals 0, for example.
This guy here, you mean?
No, at the top, like the actual.
Oh,
we actually
these
have to
ones.
restate that fact,
No,
or just
these ones you can just refer to them and just yeah, write it down.
Okay.
That's a fact that we assume that you know, like, yeah. Okay. So what about limit of the function as x goes to negative infinity? In the case of negative infinity, you should, okay, if I do the same works, then I will get with something like this, yes? But we know as if b is less than 1 and x goes to negative infinity, this is plus infinity. And it's not something that we can work with in this case. And that means that factoring the base, the exponential term with the highest base is not going to work here. We have to do the other way around. This time, we are factoring the exponential term with the smallest base. So this will be 2 to the power x. E to the power x. This will be 1. I'm just writing a little bit faster here. Okay. And now see, 3 over 2 is base bigger than 1. And as for the base bigger than 1, as x goes to negative infinity, this is 0. Similar thing is 5 over e. 5 over e is a number bigger than 1. And as x goes to negative infinity, this exponential function is going to be 0. Yes. Willow, yes, please go ahead.
Sorry, what was the reason for why you did it the other way around instead of, or you said you mentioned
You see, if I factor out the highest base, I will end up again with the exponential functions like 2 over 3 to the power x. Yeah.
Mhm.
And limit of exponential function with base less than 1 as x goes to negative infinity, this is plus infinity. But I'm looking for cases which gives me a number so that I can use limit laws.
Oh, okay.
Yes, that's why we go with this one. And in this case, actually, I can write this one as well as 2 over e to the power x. And I have, okay, 2 over e to the power x, limit of 1 minus 3 over 2 to the power x, and 1 plus 5 over e to the power x as x goes to minus infinity, as x goes to minus. Now, I know that this guy is going to be 0, this guy is going to be 0. So this part is a number, nice. I can apply limit laws there. But this guy here, this is 2 over e. 2 over e is a number less than 1. And the graph of such function is like this. As x goes to negative infinity, the function grows to plus infinity. So what I mean is that this guy will grow big and big as x goes to negative infinity. Yes. And if I have a number which is growing high, big and big, and multiplied by a number very close to 1, we'll get plus infinity. And that means that, okay, when x approaches to negative infinity, we won't have any horizontal asymptote. So this is the only horizontal asymptote that we have for this function. Again, the difference that appeared here is it should be clear when you compare these two basic facts. As 1 over x to the power alpha, x approaches to either plus or minus infinity, either case it will be 0. But for b to the power x, it's not always 0 as x goes to plus or minus infinity. It really depends on what is the base for this for this function, for this exponential function. If the function is less than, the base is less than 1, then it will be 0 if x goes to plus infinity. And if x goes to minus infinity, b must be bigger than 1, so that the function has a limit at negative infinity. That's why you need to adopt different strategies when dealing with these kind of functions for negative infinity and plus infinity. Okay. I don't have any time left here, but I'll just do one example. Differentiability, you already I assume that you have done some work, but I'm going just to use the definition for this guy to prove the find f prime at 0 if exists or not. So it means that I have to deal with this limit 0 plus ha plus h minus f at a divided by h as h goes to 0. Here, a is a is in general. This is not 0. Okay, yes. So I can write down this limit. So a plus h to the power 2 minus 2 times a plus h plus 4 minus a squared minus 2 times a plus 4. I'm just plugging in these guys into my function. And everything divided by h as h goes to 0. And here I can expand this. And I'll get, okay, a squared plus 2ah plus h squared minus 2a minus 2h plus 4 minus a squared. Oh, yes, minus times negative 2a, which is plus 2a minus 4. And when you do this, you see that this, this cancels with that, this cancels with that, this cancels with that, and everything divided by h. I have very simple function. This is a rational function in h. And as h goes to 0, this is 0 over 0. Yeah. So I can factor here. The vanishing factor is h minus 0, which is giving me h 2a plus h minus 2 divided by h. And this cancels with that. And that gives me just limit of 2a. A is a constant plus h minus 2 as h goes to 0. And that is 2a. A has no h in it, so it's constant with respect to h. This is 2a plus 0, h goes to 0 is 0 minus 2. So 2a minus 2. So f is differentiable, and the derivative of this function at a is 2a minus 2. Note that if question is asking to find derivative of function using the definition, you have to apply these steps. I know that the timing is a little bit, I'm off there, but I just want to show one thing here, at least the beginning, so that you have enough thing to work about on this one. So I have a function like this. I want to see what is happening at 0. So if a is 0, so then as h goes to 0, f at 0 plus h minus f at 0 over h. This is limit of h goes to 0. You see, f at h, if h is approaching to 0, we can assume that h is not equal to 0. When we're approaching to a number, we never allow that that variable to be equal to them, but gets closer and closer. So that means that here, since h is not equal to 0, I can use this formula. So this will be h squared minus sine of 1 over h. Oh, not minus, times. Minus, what is f at 0? Well, f at 0 is given. This is just 0 divided by h. And well, now you see this is 0 over 0, but I can cancel this guy with that guy. This was 0 over 0. And I can cancel that. And what I get is this, h sine of 1 over h. Does anyone know what is the limit of this function, the value of this limit? H times sine of 1 over h as h goes to 0.
Is it 0?
This is Fabiha. And do you know why it is 0, or what method you can use to get that 0?
You can use direct substitution, like 0, plug in 0 for h.
Yeah, but sine of 1 over h doesn't have limit. Adam, yes, please.
You can use squeeze.
This is a squeeze theorem. So we have done some work here, squeeze theorem. It tells me that this limit is equal to 0. So this means that f is differentiable at x equal to 0, and f prime at 0 is actually equal to 0. Okay. I think this is the time to stop. There were more examples. I will leave these ones for you to go over, but that's what I had to say to tell you today. Let me pause the video here.